In this video, we're going to talk about finding the area between two functions. So if you look at the diagram, we're trying to find the yellow area, and so that's the area between the function f of x and g of x, okay? Now, from A to B, remember that the definite integral will find the area between the function and the x-axis. So for instance, if we integrate from A to B the function f of x dx, that would basically give us all the area between the graph of f of x and the x-axis, okay? And if we integrate g of x from A to B, that would give us all the area between g of x and the x-axis, okay? So if we subtract these two areas, it would leave the area that is highlighted in yellow, okay? And that is exactly how we would find the area between f of x and g of x. Now, then we can use one of our properties of definite integrals and just bring this together and make it the definite integral of f of x minus g of x from A to B. And that will give us the area between the two curves, okay? So the key to this, you're basically just going to set up a definite integral and you're going to subtract your two functions. But you always want to keep it in the order upper minus lower. You want f of x to be the upper function, meaning above the other, and g of x to be the lower function, okay? So an easy way to remember this is just upper minus lower. Okay. All right, let's look at an example. So here we want to find the area of the region between the graphs of the functions f of x and g of x over the interval from 1 to 3. So I have a picture of that region here for you. And if you notice, f of x is the upper function in pink, and g of x is the lower function in blue. So when we set this up, we would want to set up the definite integral from 1 to 3 of f of x minus g of x. Now, because you're subtracting, you want to put the lower function in parentheses because you have to remember to distribute that negative, okay? So this will become the integral from 1 to 3 of x squared minus 4x plus 10 minus 4x plus x squared. And then we can just simplify this by combining our like terms. So we'll end up with 2x squared minus 8x plus 10. And then from there, I'm going to use my calculator to evaluate the definite integral. All right, so I'm just going to pause the video while I do that. All right, so after putting this in the calculator, we end up getting 16 over 3, which is the area between the two curves, okay? But again, the main focus here is just being able to set up that definite integral, okay? All right, now, sometimes you'll be faced with two functions, because remember that these are curves. So in this case, f of x is the blue function and g of x is the red function. So over the interval from A to B, g of x is the upper function and f of x is the lower function. But then from B to C, they switch. F of x is the upper function and g of x is the lower function. And then from C to D, they switch again. So if we wanted to find the area from A to D, okay, we basically have to find the area of each individual region, okay? So A sub 1 plus A sub 2 plus A sub 3, and that would give us our total area. So you're going to have to set up separate definite integrals, okay? So notice for the area for A sub 1, since g of x is the upper function and f of x is the lower, you'd want to set it up as g of x minus f of x. But then from B to C, that switches. So now f of x is your upper minus g of x, which is the lower. And then from C to D, it switches again. So g of x is now the upper function minus f of x, which is your lower function. Okay, and then you would just evaluate each definite integral and add up your area. All right, here's an example. We want to find the area between the graphs of f of x and g of x over the closed interval from -2 to 5. So again, I have a picture here for you. If you notice, from -2 to 1, f of x, which is in pink, is the upper function, and g of x, which is in blue, is the lower function. But then from 1 to 5, they switch. G of x is the upper, and f of x is the lower. Okay, so again, we're just going to set up two definite integrals. We'll integrate from -2 to 1. And in that case, we'll have x squared minus 5x minus 7 minus x minus 12. And then, of course, we can just simplify that. So from -2 to 1, this will become x squared minus 5x minus 7 minus x plus 12. And then we can combine our like terms, and we'll get x squared minus 6x plus 5. Okay, so that's kind of like a sub 1, let's say. Okay, I'm going to call this a sub 2, we're going to integrate from 1 to 5, but now we're going to switch that around. We're going to have x minus 12 minus x squared minus 5x minus 7. And then we'll distribute our negative. So we're going to end up with negative x squared plus 5x plus 7. And then we can combine our like terms. So we're going to have negative x squared plus 6x minus 5. And this would be the area for the second region, which I'm just calling a sub 2. And then I'm just going to go to my calculator and evaluate both of the definite integrals. All right, so after evaluating on the calculator, we end up with this equaling 27, and this equaling 32 over 3. And so now we're just going to add the two regions together, and we end up with 113 over 3. Okay, now, sometimes you're not going to be given the limits of integration. So to find your limits of integration, you have to find the points of intersection. or where the two graphs intersect. Without a calculator, like this example we can do without a calculator because it's not too bad. To find your points of intersection, you want to know where the functions are equal to each other, okay? So we're going to set the 6 minus x squared equal to x, and then just solve for x. So this is a quadratic equation that we're solving, so we want to set it equal to 0. We're just going to move everything to one side. And then we want to try factoring. So I would start by factoring out the negative. And then factor the remaining quadratic. So we're looking for factors of negative 6 that add to positive 1. So that would be positive 3, negative 2. And so our solutions for x are negative 3 and positive 2. So those are going to be our limits of integration, okay? Now, you also have to figure out your upper and lower function. So this is where knowing your parent graphs can be helpful, okay? Y equals 6 minus x squared, okay? That is the graph of a parabola, okay, we can switch this around, that is flipped over the x-axis and shifted up 6. Okay, so if you think about graphing or just sketching the graphs to figure out the upper and the lower function, the first one is a quadratic and it opens down and it shifted up 6. Okay, so let's just say this is 6. It's going to look something like this. And then y equals x is just your linear equation that goes through the origin. So when we found our points of intersection, or where x equals negative 3 and 2, this basically would coincide with negative 3 along the x-axis, and this point would coincide with 2 along the x-axis, and this would be the area that we're trying to find. And so in this case, f of x, or I'm going to call this y sub 1 and y sub 2. Y sub 1 is our upper, and y sub 2 is our lower. Okay, so we're ready to set up our definite integral. We're going to integrate from negative 3 to 2, and we would want to take 6 minus x squared, and for that, subtract x, dx. And then, you know, again, on these problems, the hardest part is setting up the definite integral, so I don't mind from there if you use your calculator to evaluate the definite integral. So I'm going to do that very quickly. And we end up with 125 over 6. Okay? All right. Now, sometimes instead of integrating along the x-axis, we might need to integrate along the y-axis. So here's an example. So this time, whenever you're integrating along the y-axis, your limits of integration are along the y-axis. So here we'd be integrating from c to d, okay? And in this case, you want to think of, instead of upper minus lower, you want to think of it as right minus left, okay? So f of y is the blue function, and g of y is the red function. So if we integrate f of y from c to d, that would really give us all the area between f of y and the y-axis. And then if we integrate g of y, that's going to give us all the area between g of y and the y-axis. And so again, if we subtract the two, we'll be left with the area highlighted in yellow. okay? So anytime you're integrating along the y-axis, just think right minus left, okay? Let's look at an example. All right, so here we want to find the area shaded in red, and you'll know you're integrating along the y-axis when you look at your functions, okay? Notice this is x equals y plus 2, and x equals y squared. So these are solved for x in terms of y, okay? So this time, our limits of integration are going to be the points of intersection. So we're going to integrate from -1 to 2. And we want to set it up as right minus left. Now, the right function is linear. That would be the y plus 2, because that's a linear function. And then the function on the left, that's a well, it's really like, I guess you could think of it as a sideways parabola, but you can identify it because it's y squared. So we're going to subtract y squared. Okay. So basically, this would be right minus left. Okay. And then again, now when you're putting it in the calculator, again, even though the variable is y, you can still just enter it as x in the calculator. It will still calculate the correct area. Okay, so you don't have to worry about that with the calculator. All right, and we end up with 4.5 as the area. Okay. All right, so we're going to stop there with this video, and we'll definitely practice this in class. But just keep in mind, if you just remember, if you're integrating along the x-axis, you want to set it up as upper minus lower. And if you're integrating along the y-axis, you want to set it up as right minus left. And if those happen to change, you just have to set up separate definite integrals, find the area of each, and then add the areas together. All right, you guys, have a good night. Thanks for watching.